Here we are, the geometric series. You probably don't recall this, but you've worked with this in probably algebra, maybe pre-algebra, who knows. But before we get into the geometric series, let me give you the overview of where we're at. Our main goal right now is to look at a series and determine if it's convergent or divergent. Well, how are we going to determine if a series is convergent or divergent? If you want to go based on theory, you would use the sequence of partial sums, but as I mentioned in that video, sometimes your instinct doesn't work very well, and it would take a lot of analysis to go deep into the sequence of partial sums. So the world needs rules, and we're going to go through a list of rules. This is the one we're working on today, the good old geometric series. And by the way, the geometric series is one of the three famous families of series, like the Kennedys, the Bushes, I don't know. After we're done with the three famous families, then we're going to have a list of other ways to analyze a series. But let's get on to the geometric series. This is what a geometric series looks like in symbolism form before we start filling in specific values. So this is kind of like, y equals mx plus b is the official form of the equation, but you'd rather see y equals 1/2 x plus 8. This is the official form of the geometric series, and the thing that you're going to care most about is this r, this common ratio, because it's going to lead to your conclusion about convergence or divergence. Let's take a look at one of these in action. This series, your eyeballs would look at this and you'd have to determine, is this series part of the famous family of serieses? And it turns out it is, because it's following a r to the n, a r to the n. Very frequently, if something is raised to an exponent, it's a geometric series. And here's how I know that you might remember this from your previous algebra days. You would look at a sequence of numbers and the teacher would say, is there a common difference? Meaning, am I always adding 7 to each term, or am I always subtracting 2 from each term? That was called an arithmetic series. Then you got to geometric series and the teacher said, is there a common multiplier or divisor going from term to term? Well, if I take a look at this, what I've done is I've multiplied by a half. I've multiplied by a half. I've multiplied by a half. That's what makes this a geometric series. I have a common ratio. In this case, the common ratio is 1/2. R, the common ratio is 1/2. Now it turns out, if I were to go through all of this analysis, doing maybe the sequence of partial sums, this thing would end up adding up. All of these numbers, as I go to infinity, would eventually add up to a total of 2. They'd never get greater than 2, but they would get up to 2. We could also figure that out by doing the sequence of partial sums. If I was doing the sequence of partial sums, the first one would be 1, then I would have 1.5, then a 1.75, and I could keep going on that. If I were to keep going on that, I'm going to make these numbers up. I might eventually get to a 1.97, then a 1.98, 1.989, 1.991, and you would see some sort of trend where I'm closing in on 2. I'll never get there, but I'm going to get so darn close you can't believe it. All right, well, that's a geometric series. That is a convergent geometric series. That series has a value of 2. Something important for later on in your sequence and series life is that literally you can say this thing is equivalent to. So if this thing ends up representing some function, let's just say function f of x, you would then say f of x equals 2. So a series having a value is going to be something we care about later on. So I've made up another geometric series. This one is a r to the n. I notice it's of that form. It has a common ratio of 5. If I look at this sequence of numbers, maybe the common ratio isn't as obvious in this case, but if you take some time to digest it, if I multiplied by 5, or it might even be better to think of multiplying by 5 over 1, this times 5 over 1 gives me that. Multiply by 5 over 1, I get that. Well, your instincts are good enough here. You can look at this and you're saying to yourself, I'm adding this plus a bigger number, plus an even bigger number, plus an even bigger number, and I'm going to keep that trend up going to infinity. This thing is going to keep getting a huge, huge running total, a huge sequence of partial sums total, and I'm going to be heading towards infinity. Divergent, convergent. But there's a way to get to that conclusion without going through all this mishmash of stuff, and it's memorizing this pretty easy and intuitive rule. It basically says this. Take a look at your common ratio. Is the absolute value of your common ratio less than 1? If it is, then you have a convergent series. If it's not, you've got a divergent series. It might take a little time to digest that, but it makes a lot of sense. Here's my common ratio. The absolute value of r is less than 1, because 1/2 is less than 1, and I have a convergent series because it converged on the value converged on a specific number. Here I have an absolute value of r of 5. 5 is bigger than 1. It's certainly not less than 1. So I have a divergent series. So it's going to be as simple as memorizing that rule. And that rule has some pretty good intuition behind it. If my multiplier is smaller than 1, then my numbers are decreasing as I go through the sequence. And I'm going to get a convergent value. If my multiplier is bigger than 1, then each new term in the sequence is bigger than the previous one, making my running total get out of control. Thus, it's divergent. So yes, you have to memorize this, but double yes, it's very intuitive and it's not very taxing to memorize something like that. One thing I should point out before I get back to this, I haven't mentioned it, but a couple of the examples I've used in this video or previous videos, they don't always start off at n equals 1. We can start off at n equals anything we want, 0, 1, -8, positive 17. It just turns out that most of the time we start at n equals 1, sometimes n equals 0, and that's going to come into play a little bit later on, so just keep that in mind. It's not a big deal right now. But what I'd like to focus on is this. You might have kind of wondered, why the heck are we going with the absolute value of r? Because clearly your multiplier is a positive, or your common ratio is a positive number. But it really doesn't have to be, so I'm going to show you an example that shows why we would care about the absolute value of r. Look at this beauty right here. This is quite a series, and it follows ar to the n form, so I know it's in the family of the geometric series. So I don't have to do any of this rubbish that you see over here, because I can simply say my r is -3/4. The absolute value of r is less than 1, so this is going to be a convergent series. I don't even have to do anything else. But let's pretend we were thirsting for knowledge. As I plug in progressive n's, n equals 1, n equals 2, n equals 3, you're going to notice something. N equals 1 gives me a negative result. When I plug in an n equals 2, this -3/4 gets squared, making it positive, giving me a positive second term. Third term makes this become a negative. Fourth term positive, fifth term would be negative. What I have is something we're going to come to know as an alternating series. So not only is this a geometric series, this is an alternating geometric series, but we don't have to worry about that right now. Well, now your intuition might be challenged here because I keep adding up a negative number, a positive number, negative, positive. They look like they're getting smaller, but I don't know. I have to be pretty good at fractions to know that. I could go to the sequence of partial sums. Remember, if I didn't want to rely on this rule and I wanted to think theoretically, or if they were asking me a clever question about this that was making me use the sequence of partial sums. But can you imagine trying to do that sequence of partial sums? The pain. Wait a second. You're becoming an expert at Excel. Did you know that you can set this up on Excel and get a sequence of partial sums? We've already come to the conclusion that this is a convergent series, but I'm going to show you what would happen if you were cleverly using Excel or a spreadsheet to set up the sequence of partial sums to come to the same conclusion. Okay, I don't know how well the focus is going to go here, but we'll give it a shot. So I'm setting this up on Excel, and after the first term, my value was -3, and that meant my sequence of partial sums was -3. That's that. My first term is -3. So when I go back to my spreadsheet, this should be my next term, my next term, my next term. I haven't done the sequence of partial sums. So here we are back on the Excel readout. There's my next term. The sequence of partial sums is the previous total combined with my new term. And as I go through here, you'll notice that the terms of my series, or the sequence of terms, is alternating positive and minus. And as I'm doing that, Excel's doing the work for me to add up the sequence of partial sums. So it's simply taking the previous running total and combining it with the latest new term. But remember, if this is going to be a convergent series, the sequence of partial sums should be closing in on a very specific value. And as I go down here, your eyeballs or your instinct might be telling you that yes, we are closing in on a specific value. Look what happens by the time we get out to the 20-some terms. We're already starting to hover around -1.72, -1.71. We could go more decimals if we wanted, and we can go further down the line because, heck, we're not even close to infinity yet. But for our purposes, it seems like we're closing in on a number because the sequence of partial sums is closing in on a number. So I might even be brave enough to say that this series, hold up. Okay, I might even be able to be brave enough to say that this series has a total of, not question mark, but -1.71. I might be off by a decimal or so, but it's definitely convergent because the rules of the geometric series told me so, and the sequence of partial sums told me the value of that series. Hope you enjoyed this.